Hello, Jordan.
Hello.
Hey.
How are you?
You? Yeah, I'm doing good. Thanks. There's no one in the class yet. I realized that we don't have class Tuesday, and then on Thursday we have an exam.
You're talking about next week?
Yes.
Yeah. I'm gonna be very, very pressed to get there. I'm
Yeah.
pretty behind on everything at the moment.
Yeah.
I took the day off work today completely, and I'm gonna be sitting down and trying to get everything I can caught up. I want to be ready and prepared for the exam.
Yeah. I can imagine. Yeah. I think this is time of the semester also. It is, of course, you had more things going on, but even otherwise, I think most of the students get very loaded during these weeks. I think between 9 and 12, I think ninth week to 12th week is the most demanding, I think, because things pile on.
Mm-hmm. Yeah, I'd like to be able to do all the homework assignments at least, even if I can't turn them in on time. I'd like to get through them before the exam and have watched all the lectures that I missed and just studied extra beyond that so I feel prepared. Because I don't want to just get to the exam where I've only been able to watch the lectures and do the assignments. I need, personally, myself, I have to do more in order to be prepared.
It's yeah. Okay, so we have Luke and proceed. Okay, I think I was telling Jordan that I did not realize that there's an exam next week and we don't have class on Tuesday, so I should finish at least a little bit so that is things are in. At least the homework is doable. That's the point.
I see.
Because homework is due on Thursday. When I made it due, I didn't realize Tuesday was a holiday, but I think we can still get it done. Or the content can be done this week, this lecture, and then later I can elaborate on that. Okay. So. Move the camera. So we have homework 8. That is due. Earlier too. On this is Thursday. This is the day of the exam. So the homework is, of course, due on the day of the exam, but the homework is important. That's why I'm making it due on the day of the exam. But at the same time, the due date is flexible. So if you're, this doesn't have to be priority. but understanding the material is priority. So in that sense, you have to be able to do that. So you should do that, and you should not give it due importance. So I don't know how to say that. Yeah. So we have Khaled too. So we're missing most of this. Yeah. Okay, so what we did last time is we were talking about a Green's function, right? The differential equation, a particular differential equation we are considering is that of a driven harmonic oscillator. The minus becomes a plus. Is that minus? That's really minus, right? Check. How does that work?
It should be minus if you do it the same way you did it with the Laplacian. Pretty sure.
Let me see. Because I took an overall sign out. Right? So let me just check it quickly. So we have d square over dt square of x is equal to omega naught square times x, right? That's it. So when it comes on this side, no, this is minus, right? If a harmonic oscillator has a minus sign on it. So when you take it onto the left, that becomes a plus. And from that point on, this is an overall sign because the harmonic oscillator actually is a homogeneous differential equation. And I define that with a minus sign, and the forcing function, this is not really a force because I divided out by Gauss. So force divided by the mass of the object. So that's the forced harmonic oscillator. Right, that's the differential equation we are talking about. And we said that homogeneous, if we know the solution to the homogeneous differential equation, we can find the solution to the inhomogeneous differential equation using the idea of Green's function. So the point is to define a new differential equation, keep everything the same, except that the source, instead of it being an elaborate function, just make it a delta function. So this is now Green's function. Right? So this is g of t comma t prime. I think in your notes, or actually we keep it capital G. Right? In your homework and other places, it is t comma t prime. In my notes, basically. In electricity, in electrostatics, I try to use the small g because you start with the capital G, then you Fourier transform it, and then that's what is called the small g. This is, as you notice, this is not a complete source. This is a source that survives only at t equal to t prime, and its amplitude is a unit amplitude. So the weighted average of these quantities gives you the actual source. In electrostatics, the corresponding or analogous thing would be a point charge of unit magnitude. So that's the idea of Green's function. And last time we elaborated a few properties of the Green's function, but the take-home message is, if we know the Green's function, what's actually the solution of x of t? It is the following. X of t is equal to, you can always have the solution for the homogeneous part. You cannot avoid that, but that is also necessary because you need boundary conditions, right? So there's a times e raised to, the solution for this is e raised to I omega t, omega naught t plus t times e raised to minus I omega naught t. Notice this particular solution, or not, I should use the word particular. Particular is the technical word for a solution with respect to the source. This solution that I have written actually satisfies the homogeneous differential equation. So nothing can stop me from adding that, right? Because this, if you substitute this in that, the left hand side is equal to 0. So as far as one of the terms gives you the right hand side, you're good enough. And that particular term, which is called the particular solution, is got by et prime times g of t comma t prime times the source. And you go from the whole domain of on which the time is defined. So that's your general solution for your for the function x that you're solving for. Remember, a differential equation always comes with plus boundary conditions, right? So this is boundary conditions are x of 0. And this is typically given as a number with some units associated with it. But let's say to keep it general, this is x naught. Notice the difference is very similar. This is x as a function of t evaluated at t equal to 0. I call it the subscript x naught. And the velocity, which is the derivative of x time t equal to 0, I call it v naught. Like that's your initial condition. So if you want, that's your boundary conditions. Or in this case, you will call it the initial condition because it's a time. And A and B here are determined using your initial condition. So this is a general solution, and A where A and B are determined using initial conditions. So how does this work? So let's explicitly solve this. Let's start from this Green's function equation, and let's see how we proceed to do that. Notice there are initial conditions, and from this point on, we are also going to derive what will be called continuity conditions, and pay close attention to what it means to what is meant by continuity condition. So let's start with a differential equation. So at this point, this is just a differential equation for a new function. It is not the old x of t, so it's not very obvious what are the initial or boundary conditions for the Green's function. So we leave it completely open, and the point is that the equation, the Green's function equation itself has boundary conditions inbuilt in it. And what are those? So first, let's integrate this equation. So let me go to the right side of the board. So integrate that equation. So before that, maybe I should draw a line here just to give you a picture of what's happening. That is a time t. So this is a line along which time t is measured, and somewhere there is t prime, right? T is equal to t prime. So let me not even say t equal to. So that's t prime. That's a very specific value. That's the time at which the source exists. Otherwise, it's 0, right? This is a delta function. The right side is 0 for t prime less than 0, and it is greater than for time greater than t prime, it is still 0. So using that feature, so let's immediately write that this is equal to, so we have t square plus omega naught square t comma t prime is equal to 0 if t was less than t prime. So let me say that's t less than t prime. And the same thing for t greater than t prime. So notice that these are homogeneous differential equations. So I know how to solve them. The delta function was not very obvious how to solve them, but these two individual cases are solvable. Oh, we have Michael here, or is it Moses? No, Michael. Okay.
Hi.
Sorry, back or?
Yes.
So now you're married, I guess?
Yep, it happened.
Okay, cool. Okay, congratulations.
Thank you. It was really nice. It was really fun.
Good. So did your wife get to come back here, or do you guys have to still go separate ways?
Yeah, we're still separate. She's still in Kansas.
Okay. Yeah, but it's only 2 weeks more, I suppose. There are some holidays coming.
Right. Yeah, she won't move to Illinois until end of May next year.
Okay. Good. Okay. So we are doing Green's function. Here we want to solve a differential equation of this kind. We introduce a new equation called the Green's function, which survives only at one time. But that equation has this feature that at t less than t prime, it's a homogeneous differential equation. At t greater than t prime, that's also a homogeneous differential equation. So I can solve these two cases separately. And the idea is going to be stitching it. So we know the solution here, which is homogeneous. We know the solution on the right, that's also homogeneous. And then we want to match it. So that's going to be called the continuity conditions. So we want to match the solutions at that point t prime. And then the question comes, how do we match it? And we will talk about that. But to immediately, we can say that this implies that, or let me, yeah, I might be able to squeeze it in here. So this implies that g of t comma t prime has two solutions. That's a times e raised to I omega naught t plus b times e raised to minus I omega naught t. And this is c times e raised to I omega naught t plus d times e raised to minus I omega naught t. This is for t less than t prime. And this is for t prime less than t.
So I have a quick question. When you define it on a line like that and you say t greater than t prime or t less than t prime, how does it exactly make it different than negative infinity to infinity when they still both equal 0? I'm a little confused by that.
No, I'm not saying that it is, see, time still goes from minus infinity to plus infinity. So this is somewhere here is t is equal to plus infinity. And somewhere here is t is equal to minus infinity, right? That's your domain. Right? That's, if you want, that's your domain of time. Somewhere there is a source. In particular, if this was a continuous function, the source is there everywhere. At every point, it is getting disturbed. But the Green's function says that let me isolate the disturbance. Let me isolate the disturbance to at some arbitrary time t prime.
Okay.
And then let's ask, how does this particular, just one moment of disturbance give you the solution? And if I know one disturbance, then I'll keep adding on to that. Right? If I keep adding all the disturbances, that's what this addition is. This is one disturbance. Add up all the disturbances with the weightage given to that, that gives me the total function, total solution. Does that help?
Yeah, I was just thinking the answer would be the same as if you just treated it as continuous, but
Yeah. Okay.
okay.
If it's not clear, ask me again. I can repeat that.
No, I think I got it. I understood what you said. You're trying to isolate at t prime
Exactly.
and then add up the components along to,
Exactly.
yeah.
That's correct. So currently our goal is just to get the solution for an isolated kick, if you want, like this is a disturbance, right? Isolated kick at t prime. And for that purpose, I say that since it is isolated at t prime, before t prime it's homogeneous, after t prime it is homogeneous. I know how to solve that. That's your two solutions. And then the question is, how do you match them, right? At t prime, is there any conditions? Because now you have got 4 independent arbitrary parameters, right? And at the most, we can fix 2 of them from here. If you have 2 boundary conditions there, or 2 initial conditions, you can think of fixing that. Oh, actually, I should be careful, right? I use the same notations. So let me call this alpha and beta, right? Let me call this alpha and this be beta, right? So overall, notice how many parameters do you have? Alpha, beta, A, B, C, D, 4 plus 2, 6. And we have only 2 initial conditions. So what's going on here? Correct. So that's what we are trying to see. It seems like we have elaborated the problem, but let's keep going on. There is 2 more conditions we can see. So let's do that. So if you want to solve this now, I have to put some conditions on A, B, C, and D. For that, I need to learn some conditions. And for that, I go back to my equation and I integrate that equation. I integrate this equation from dt. And since so there's a t prime disturbance, right? Remember your electrostatics, if you integrated on the source, it contributed. If you're not on the source, it doesn't contribute, right? That's a property of a delta function. So I want to go somewhere very close to this point. So this is t prime minus delta. Let's say delta is a positive constant, small constant. So I want to go from t prime minus delta to t prime plus delta. So I'm going to integrate from t prime minus delta to t prime plus delta of the whole equation. And on the right hand too. dt delta of t minus t prime. What is the right hand equal to? Right hand side equal to? What's the right hand side equal to?
Just the charge, like the charge at that point.
Yeah, but here we are talking in terms of time. Delta function so is 1, right?
Mm-hmm.
Yeah, correct. You will capture the charge because you're having electrostatics in mind, but this is just a delta function, right? So it's just 1. But good, I think the answer is correct. So this is just 1. Right. Okay, so that's good. What is the first term here? So let's explicitly do that. So this is t prime minus delta. This is t prime plus delta dt, and that is a total derivative. Remember your electrostatic surface terms, right? So this is your divergence theorem if you want. So this survives only on the surface. This is a total derivative, that's dt. I can cancel this out, and this gets evaluated only on the boundary if you want. And let me put some space there. So minus omega naught square times t prime minus delta t prime plus delta t prime times g of t comma t prime is equal to 1. This is a total derivative that survives only on the boundary, but what is the boundary here? We are going very close to t prime. We are just barely on the left hand side and barely to the right hand side. So this is the discontinuity if you want. So this is the discontinuity in the Green's function. So this is evaluated at t equal to t prime plus delta, and t is equal to t prime minus delta. That's the discontinuity in the derivative of the Green's function minus omega naught square times, when you integrate it over the Green's function, prime p of t comma p prime is equal to 1.
So can you explain to me what happens to the extra like derivative there? On the left-hand side, you have dt times d over dt. So I understand what happens to the dt's, and then you have d squared g.
Remember that integral of dt of d by dt of f, any function f, correct?
Mm-hmm.
Going from t1 to t2 is equal to f of t2 minus f of t1.
Oh, yeah. Okay. Yeah. Okay.
This is just a way of writing. So you say that this is f of t, t2 to t1.
Okay.
Right? So since it's a second derivative, first derivative acts to cancel that. So that tells me that that's a surface term. It survives only on the surface, right? Like think of conservative forces, right? Conservative forces survive only on that boundary. Right? But this has probably this has some connection to that, but that's not the point. This is just a total derivative. Okay. Okay. So now at this point, I need to make some argument. You can do this more thoroughly, but I feel that it doesn't give too much insight. It's a lot of algebraic procedure. But let me make an argument here. So notice, first of all, G. So you have first point is that we can say G is finite. So we are all talking about at t equal to t prime. So G could be, G is finite. That means to say that it is not infinite, or G could be infinite. At t equal to t prime, it really blows up to infinity. If that is the case, if this was actually infinite, this second derivative, notice what we have our equation to be. This is G plus omega naught square times G is equal to, so there's a minus sign, there's a minus sign, and there's a delta function. If this was having an infinite discontinuity, the second derivative of that will be much more singular than what it is already is. Like if this already had a discontinuity at t equal to t prime, first derivative will pick it on, so that will become a derivative of a delta function, and the second derivative will become a second derivative of a delta function. So you couldn't get a delta function. So again, maybe I should clarify. Remember, your step function is this, correct? So this is what we want to keep in mind. Suppose you have a discontinuity of this kind. If I were to take a derivative of that, this will give me a delta function. Right? A second derivative of that will give me a delta function of this kind. So that's a derivative. So this is a step function. This is a delta function. And that's a derivative of a delta function. Okay. Now, it's possible that the green function set it has any one of this kind of discontinuities, but since the right hand side has a delta function to begin with, that suggests that we are somewhere here. That means there is only a finite discontinuity in here, because if there was an infinite discontinuity, a derivative of that will be not a will not be a smooth delta function, and a second derivative will surely not be a delta function. So that's an argument to propose that G actually, so the argument I'm making is that G at the most has a finite discontinuity. This can be more rigorously algebraically proved. By algebraically, I mean instead of giving this argument, you're always not sure, oh, did I miss something? But you can actually multiply this whole Green's function by time t and then integrate it and get a similar relation. And you can actually prove this. So the point is G, I'm not saying it is continuous. It has a finite discontinuity. We don't know whether G is continuous or not. And we will see what it is. Okay. So, but then is it having a finite discontinuity? Right. So let's suggest that, because, oh, again, that's right here, right? If the Green's function has a finite discontinuity, that's somewhere here like this. Right? So that's a finite discontinuity. First thing I did is that I ruled out infinite discontinuities, but now this is a finite jump. If there was a finite jump, again, so that's your Green's function. So if I take the second derivative of that, that's a first derivative. Second derivative is not a delta function. It's giving me a derivative of a delta function. So that's also not possible, right? Even a finite jump is not possible. But what is possible is that G is continuous, but its derivative is not continuous. So typically the Green's function is of this kind, right? So this is a function. It has a bump in the sense that, think of it as a bump, right? I mean, actually a source, right? As the function was smoothly going, someone came and kicked it, right? It's like an elastic collision kind of. So something was happening, but that's not actually the graph here, but this is an actual time graph. So there is a function here, there is another function. It doesn't have to be a straight line. This could be going like this. This could be going like that. And its derivative has a, so this is continuous, so G is continuous. So G is continuous.
So it's continuous but not differentiable, but like that.
Not differentiable, or it's different. Its differential, or its first derivative is not continuous. Yes, it is not differentiable at that point. Correct. So, but G derivative of G is discontinuous.
So it's discontinuous only at t prime, but it's continuous everywhere else.
Everywhere else, that's correct. But then one wants to know what is the discontinuity, right? So let's say now, if so, I've made an argument here. So argue that G is continuous. At t equal to t prime, which again can be proved algebraically also. But if that is the case, if it is continuous at t prime, or for that matter, I can do this, considers any function now, right? So this is some function here, and this is more than continuous. This is having a finite discontinuity, right? So this is your f of t, let's say, as a function of t. Now I am concentrating on this piece here. This is an integral of the function from t prime minus delta to t prime plus delta. So let's say this is t prime. And there's a jump there. And let's say this is t prime minus delta. And that's t prime plus delta. So when I do this integral, I'm basically doing this integral here. Okay. What is that integral in the limit delta tends to 0? What is that area equal to if I take the limit that's getting squeezed?
1.
1. Why do you say 1?
Oh, no, 0, because
Yeah.
it's not, and I was thinking of the delta function.
Yeah, there is no delta function here, right? So this is, we said is actually having a continuous point there. So this integral is actually 0, right? Area tends to 0, which means this whole box is tending to 0. Okay. So if that's gone, I know the discontinuity in G exactly equals 1, or the negative discontinuity in G is exactly equal to 1. So if I convinced you on that, so we first argued that G is continuous. So that means to say, so that's the first. So first condition is that G of t comma t prime evaluated at t equal to t prime plus delta and t equal to t prime minus delta is equal to 0, right? F of t minus of t is equal to 0. That means it's continuous. And the second one, if that is the case, then this goes to 0 and its derivative t comma t prime evaluated at t equal to t prime plus delta, t is equal to t prime minus delta, that's equal to -1. So its discontinuity is exactly -1. That's your two conditions. These are called continuity conditions. So these are called continuity conditions. These are not, by the way, not always true for every Green's function. This is a differential equation dependent quantity. You're doing some other problem, you will have to again derive these continuity conditions. These are dependent on your equations. Sometimes they're directly boundary conditions, sometimes they're Neumann boundary conditions, so you should be careful what it is. There are cases when this will be continuous and this will be discontinuous. So there are various possibilities possible, but this is the most common one. Like because harmonic oscillator is very common, most of the time we'll be dealing with this. This is continuous, continuity conditions.
So since they're continuous, say you have more than one, you're looking at more than one Green's function, you can just do the superposition of them and add them. Does that work?
Yes. So the point is, I solved this for a t prime, right? Where t prime was arbitrary.
Mm-hmm.
Right? And then I add up all the values of t prime. That's the superposition principle. since it's a linear differential equation, I can add up the solutions,
Okay.
right? And when you're adding up, you give it weight, right? That's your function a of t doing. If this source, the source at this point was stronger, you give it more weight. If this was a weaker point, you get less weight. Once you have a solution, then you just add up using superposition principle. Correct? Is that your question?
Yeah, I was just thinking about in a problem sense where you're given two G's that aren't the same. Where you're given.
No. Okay. So good. Okay. That goes back now. If you have two Green's function, work with one. Okay. It doesn't matter. Remember that particular. So this is a particular solution. If you know one solution, the other solution is also fine. It will be off.